Imagine a world where your smartphone's motion sensor is so sensitive it can feel the quantum jitters of a single nanoparticle without needing a freezer the size of a refrigerator. Sounds impossible? That's exactly what a new breakthrough in room-temperature quantum optomechanics just pulled off, and it's shaking up everything we thought we knew about cooling, sensing, and the very boundary between the quantum and classical worlds. But here's where it gets controversial. For decades, physicists insisted that if you wanted to see quantum behavior in anything heavier than a few atoms, you had to plunge your experiment into a cryogenic deep freeze. The logic was simple. Heat is the enemy of purity. Every stray thermal photon acts like a rowdy concert goer, drowning out the delicate quantum whispers you're trying to hear. So labs spent millions on dilution refrigerators, liquid helium plumbing, and vibration-isolated tables that look more like steampunk submarines than scientific instruments. And this is the part most people miss. The new work turns that dogma on its head. Instead of fighting thermal noise by brute force cooling, the team found a loophole: quietly decouple the vibrating nanoparticle from its hot surroundings altogether. Picture a tiny, asymmetric grain of glass, really a cluster of 120 nanometer silica spheres, floating in a vacuum chamber like a miniature space station. A single laser beam traps it, not by clamping it to a cold finger, but by levitating it so gently that the only thing touching the particle is light itself. No physical anchor means no heat-conducting bridge to the room temperature world. The magic ingredient is a high-finesse optical cavity. Think of it as a microscopic whispering gallery for photons. When the nanoparticle twists ever so slightly, it scatters light into this cavity in a process called coherent scattering. By tuning the cavity resonance to the blue sideband, a fancy way of saying the photons steal energy from the motion, the system siphons phonons out of the nanoparticle's rotational mode faster than thermal noise can sneak back in. The result? A motional ground state occupation of just 0.04 phonons, translating to a jaw-dropping 92% quantum purity at room temperature. Let that sink in. Even the best cryogenic gigahertz resonators, lovingly cradled at millikelvin temperatures, top out around 85% purity. The levitated rotor just beat them while sitting on an ordinary optical table. Of course, skeptics will ask, isn't this just a parlor trick for one very specific motion? Fair point. The experiment focused on a single librational, twisting, mode oscillating at 1.08 megahertz. Yet the same toolbox, phase noise cancellation via an active feedback noise eater, sideband resolved cavity cooling, and exquisite heterodyne detection, can, in principle, be multiplexed to tame all 6 mechanical degrees of freedom of a levitated object. Imagine 6-dimensional quantum control of a nanoparticle's position and orientation, all without a single cryostat. Controversy alert. Some traditionalists argue that levitated systems trade one devil for another. Yes, you dodge cryogenics, but you invite laser phase noise and radiation pressure shot noise. Quantum backaction that can heat the motion just as surely as a warm gas. The authors counter that active noise suppression plus coherent scattering geometry keeps intracavity power low, sidestepping mirror heating that plagues clamp devices. Who's right? The jury is still out, and the debate is heating up faster than a nanoparticle in a bad vacuum. So, what could you actually do with a 92% pure, room temperature quantum rotor? For starters, it's a pristine testbed for sensing ultra-weak torques. Think measuring the twist imparted by a single electron's magnetic moment, or hunting for deviations from Newtonian gravity at micron scales. Push further, and you can prepare exotic quantum states, squeezed angular wave packets, superpositions of clockwise and counterclockwise rotations, or even Schrödinger tennis racket flips that never damp out. And because the oscillator lives at megahertz frequencies, it could be resonantly coupled to trapped ions or superconducting qubits, opening a direct quantum bus between light, motion, and matter. The takeaway? the cryogenic monopoly on quantum optomechanics just got shattered. Whether you view this as liberation from dilution refrigerators or a risky gamble with laser noise, one thing is clear. The quantum frontier no longer requires a parka. Now, over to you. Is room temperature quantum control the future, or will cryogenics always have the last laugh when it comes to ultimate purity? Drop your hot or cold takes in the comments. Let's keep this debate spinning.